Welcome to qnawire.
For this problem on the topic of rotational motion, we have a uniform solid cylinder which has a radius 2r and mass m resting on a horizontal tabletop. It is attached by a string through a frictionless axle to the center of the cylinder so that it can rotate about the axle. The string runs over a disc-shaped pulley which has a radius r and mass m, and this is mounted on a frictionless axle to its center. Now, a block of mass m is suspended from the free end of the string, as we can see in the figure. We want to find the magnitude of the block after the system is released from rest. Now, we'll use the conservation of energy to relate the speed of the block to the distance it has descended, and then use a constant acceleration equation to relate these quantities to the acceleration. Now, for the cylinder, we have its moment of inertia IC to be a half times m times 2r all squared. And for the pulley, we have a moment of inertia IP, which is a half m r squared. And the total kinetic energy of the system, K, is equal to a half into mv squared, which is the translational kinetic energy for the cylinder plus the angular kinetic energy for the cylinder, m times 2r squared over 2 times v over 2r all squared, which is I times omega squared, plus the angular kinetic energy for the pulley, which is mr squared over 2 times v over r all squared, plus the translational kinetic energy for the block, which is a half mv squared. And so this gives us a total kinetic energy for the system of 3 over 2 mv squared. Now, this kinetic energy must be the work done by gravity. And so if the hanging mass descends a distance y, then we get that this kinetic energy must equal to mgy, which means that v squared is equal to 2 over 3 g times y. Now, for a constant acceleration, we know that v squared is equal to 2ay. And so we can equate these two expressions, and we get the acceleration a to be g over 3.